All right, so this problem says a rigid body with a cylindrical cross-section is released from the top of a 30-degree incline. It rolls 10 meters to the bottom in 2.6 seconds. Find the moment of inertia of the body in terms of its mass and radius r. All right, so here's the 30-degree incline, and here's a cylindrical body that's rolling without slipping. Okay. Now, if you had an ice cube sliding down frictionlessly, the acceleration of this ice cube would be, I'm sorry, g sine theta. Okay. Now the acceleration of this guy, the acceleration of the center of mass of this guy, what's that? The acceleration would be g sine theta, the same as for the ice cube, divided by 1 plus I center of mass divided by mr squared. Okay, so you see this is not 0. This would be 0 for a point particle, but this is not 0, so this number is greater than 1. So this thing accelerates down slower than an ice cube. Okay, that means this will take longer than an ice cube to reach the bottom. Okay, so larger this number in the denominator, longer it takes. You guys understand?
Can you say that again? I'm sorry.
Okay. Larger this denominator, lower the acceleration, longer it takes to get down.
Got it.
All right. All right, so what we'll do is now, okay, so here's our x-axis. Our x-axis will point this way, and it rolls to the bottom in 2.6 seconds. So it travels 10 meters in 2.6 seconds, and find the moment of inertia of the body. All right, so we'll use this formula, v naught t plus 1/2 8t squared. Okay. Initial position is 0, final position is 10 meters, so that would be 10 meters. It rolled down 10 meters, so this would be 10 meters. Initial velocity is 0. That term will be 0. 1/2 8t squared. Okay, so this is 10 meters equal to, this guy is 0. Okay, so acceleration is 20 meters. All right, so the acceleration of the cylinder is 2.696 meters per second square. Okay, now we'll plug that in here. Okay. So 1 plus I center of mass mr square equal to g sine theta divided by a. We just found a. Okay. So what we're trying to do is find the moment of inertia of the body in terms of m and r. So we're trying to find this guy, okay? So now we have a number for this. All right, so everybody with me so far? Yeah. So let's copy this. So 1 plus I center of mass m r square equal to 9.8 sine 30 divided by 2.96. Okay. So this number on the right works out. Okay, so I center of mass over mr square is 1.66 minus 1, which is that, okay? So I center of mass is 0.66 mr square. All right, now we'll give meaning, okay, so you want to think about this carefully, we'll give meaning to this number, okay? So I'm going to give you, you can look these up in tables. For a uniform cylinder, that is a cylinder where the mass is uniformly distributed, whose density is uniform, I center of mass is 1/2 mr squared. For a wheel where the mass is all at the edge, the I center of mass is mr squared. You guys understand? So remember, the further the mass is distributed from the axis of rotation, greater the moment of inertia. For a solid cylinder, where the mass was distributed evenly here, that number is 1/2. For a bicycle wheel, that number is 1. For your cylinder, this was 0.6. Greater than 1/2, less than 1. You guys understand? So the mass is more distributed more toward the edges. It's not quite a bicycle wheel, but it's closer to a wheel than a solid cylinder, okay? Did you guys understand that? So that's what those numbers mean, and that's what we found that for, okay? Any questions? All right. A solid cylinder rolls up an incline at an angle of 20 degrees. If it starts at the bottom with a speed of 10 meters per second, how far up the incline does it travel? Okay. So this is a 20-degree incline. This cylinder is rolling up, and its initial velocity, center of mass velocity, is 10 meters per second. Okay, so our x-axis will point that way, and so on. Okay. Which way is it accelerating? So this is a solid uniform cylinder. So the acceleration in that direction, the acceleration of the center of mass is, we just saw that formula, g sine theta divided by 1 plus I center of mass mr squared. Now for a solid cylinder, what is I center of mass? The moment of inertia about the center of mass, 1/2 mr squared. Okay. So the acceleration will become, okay, this is 1/2 mr squared. The mr squared will cancel. you have a half, 1 plus a half. One plus a half is 3 halves, so you get that. All right, so let's calculate this fella. 2/3 G is 9.8 sine 20. Okay, so what is this number? That's the acceleration of the center of mass of this wheel in this direction, okay? And this was the initial velocity in that direction, okay? So now we'll find out how far it goes up. So we can use this formula. How about we use this one? V square equal to V naught square plus 2a x minus x naught. Okay, what does this formula give you? That's the final velocity and that's the displacement. What do you want for the final velocity to be? What is the final velocity? I'm sorry? Very good, 0. It's come to the incline and stop. Okay, very good. So this guy is going to be 0 for us. Yeah. X minus x naught will be, okay. So minus 10 square times 2 times minus 2.25. The acceleration is negative, okay, and this will come out in meters. Okay, so what we have found is a cylinder rolling up a 20-degree incline. If it starts off at 10 meters per second, 10 meters per second is about 25 miles an hour, and it will go up 22 meters. 22 meters is roughly the width of this room. So an incline starting from the bottom of the floor to the ceiling, it would reach that up, far up. Okay? So you could roll a solid cylinder like that. You guys understand? Okay. Yep. So this problem says a Formula One race car with a mass of 750 kgs is speeding through a course in Monaco and enters a circular turn at 220 kilometers per hour. So we'll convert those to meters per second in a second. In the counterclockwise direction about the origin of the circle. So here's the curve. equal to 220 kilometers per hour. A kilometer is 1,000 meters, 1 hour is 3,600 seconds. So divide this number by 3.6 to get it in meters per second. Okay? Okay. And the radius, what was the radius? Enters a circular turn in the car. The radius of curvature of the first turn is 330 meters. And that of the second turn is 100 meters. Compare the angular momentum of the race in each turn. Okay. So this is the first turn, this is the second turn. In the second turn, this is V1. V2 is 180 kilometers per hour, which is 50 meters per second, and R2 is 100 meters. All right, now what the problem is asking you is compare the angular momentum. Okay, so the angular momentum, if you look, so we are going to treat this car as a point particle, and the angular momentum when you go on a circular path is mvr. Okay, mass times the velocity times the radius. We'll calculate that, L1 and L2. All right, so, okay, let's go ahead and do that first. So L1, angular momentum in turn 1, is mass is 750 kgs. Velocity is 61.1 meters per second. And radius was 130 meters. Okay. Okay, so that's the angular momentum. And L2 similarly is 750 kgs times 50 meters per second. All is good? All right. So the angular momentum on the second curve is, around the second curve is kg meter square per second. All right, now the problem doesn't ask us this, but what we'll do a little bit of extra, okay? So when when the car is going around the bend, is it accelerating?
Yes.
What kind of acceleration does it have?
It's tangential. No, I'm sorry. Centripetal.
Very good, my friend. Because the direction, even let's assume that its velocity is constant, that no, its speed is constant, the direction is changing, and so it's got centripetal acceleration. So let's calculate that. Okay? So we'll calculate A centripetal 1 and A centripetal 2. Okay? Okay. So 61.1 meters per second. And of course, we want to write it in terms of G's in, okay, so 2.93 G's. So that's pretty amazing. He's being pushed, the driver is being pushed to the toward the center of the circle with 3 times his body weight, his or her body weight. Okay, 3 G's, that's pretty good. All right. Okay, so all right, AC2 is that. All right, what's going on here? So on the first turn, he's pulling 3 G's, and here he's only pulling 2.5 G's. What happened? So the G's tell you how sticky his tire is, how fast it turned. His tires are still sticky here. Why did he slow down? He could have taken that turn faster, is my point. Hmm? I'm sorry? So? Less roomy, probably. Okay, so these guys are trained to push the limits. Okay? And it's not like his skill went down. So it probably there wasn't enough room, and it was a crowded turn. Yeah. What's that? No, well, also look, when they're going faster, they probably separate much more. At a slower speed, it gets very crowded. Everybody catches up. All right. So, again, the point is there are stories hidden inside the numbers. Okay? And that's what you gotta learn to decipher. Did you guys understand that? All right. All right. So this problem says, at a particular instant, a 1 kg particle's position is that, its velocity is that, and the force on it is that. what is the angular momentum of the particle about the origin? So all these vectors, the position vectors with reference to the origin. And this problem is is about doing cross products and looking up definitions. So angular momentum is defined as r cross momentum. Okay, so it's r cross mass times velocity. Okay, where r is the vector from the point about which you're calculating the angular momentum. You can calculate the angular momentum about any point. Okay, so r would be that vector. So if you're calculating the angular momentum about the origin, then r is a vector from there. Okay. All right, so let's calculate this cross product. Okay, so L is mass times r cross v. M is 1 kg. R is 2I minus 4j plus 6k cross V is minus I plus 4j plus 1k. Okay. And so I'm going to write the units here. Kg for mass, meters per second. So kg meter square per second. All right, now it's just a matter of figuring out the cross product. Okay, I'm going to give you the formula for it, but I'm going to show it to you two ways. By the way, anybody remember the cross product formula? Okay, go ahead.
A cross B.
Right. You remember the formula?
Absolute value of A times absolute value of B times the sine of B.
That's the magnitude.
Oh, I'm sorry.
Yep. Very good, though. Very good. So A cross B. I'll show you two ways, by the way. So this is easy to remember. Okay. I, J, K. Okay, those are the unit vectors. Okay. So here's the deal. When you take your right hand, okay, and when the first finger, your thumb turns into the index finger, the middle finger points in the direction of the cross product. Okay. So here's I cross J is K. J cross K is I. K cross I is J. If you go in the other direction, I cross K is
J.
negative J.
Okay.
K cross J is negative I. Okay? All right. So let's do it that way. Okay, and then I'll show you the other way. And then I'll give you the formula. Okay. So here's one. I cross I is 0. I cross J is K. So that is 8K. Then I cross K is minus J. Okay? I cross K is minus J, so that's minus 2J. Okay? Everybody comfortable with that? Good with that? Okay. Karina, J cross I. Very good. So that's minus 4 times minus 1 is plus 4, but then you have a minus K. So minus 4K. All right. You're on a roll, Karina. for J cross J.
So what?
What is J cross J?
What? Or zero?
0.
Zero.
Yep. J cross K, my friend.
So it's
Yep, very good. Okay. So that's minus 4i. Okay. All right. All right. Evelyn, K cross I. Hello? No? You're still on spring break. All right, my friend.
J.
K cross I is J. Very good. K cross I is J. Okay? And so that's minus 6J. K cross J.
Is it negative I? Minus I?
Very good. Negative I. K cross. All right. So that's minus 24i. And K cross K is, of course, 0. Okay? Any vector crossed with itself is 0. Okay? All right, now you can just collect the terms. So this is minus 28i minus 8j plus 4k. And the units are kg meter square per second. Oops. All right. What is the torque acting on the particle above the origin? Okay, so we will do that the other way. Okay. So there's the angular momentum. Any questions on this?
I do have one question. On the trying to find which one it was. The negative 4j and the negative I,
Mm-hmm.
it still creates a negative because it's double, right? You have j cross I, which makes negative k, and you also have the negative.
So minus 4 times minus 1 is plus 4, and then you get the.
And then the negative from
yeah.
the orientation.
Yeah,
Okay.
All right, so now let's do part B. Torque is, okay, so the deal is whatever point you calculate the angular momentum about, that's the point you want to calculate the torque about. You can't calculate the torque about one point and angular momentum about this other, some other point, okay? Then it won't satisfy Newton's second law. Okay, so R is, again, the same vector. R is 2i minus 4j plus 6k. Cross force is 10i plus 15j. And we can write the units Newton meter. Okay, so for torques, you leave this as Newton meters. In another context, these are the same units for work, and you name them as joules. So for torques, you don't name them as joules. You leave it as Newton meters. Okay. All right. So we could do the same thing, I cross j and so on. But now I'll use this formula just to remind you of the formula. A cross B equal to AY BZ minus AZ BYI plus AZ BX minus AX BZJ plus K AX BY minus AY BX. You guys remember this formula? Okay. All right, now we're going to use this. All right. Gabriel, you're going to help me out. Actually, you and Eliza. All right. Who wants to go first? You go first.
Okay.
Do the x component.
The I component. Okay.
The I com- mhm.
Negative 4 times 15 minus.
Whoa.
Oh, wait.
BZ is 0.
Easy is 0. I'm sorry.
Yep.
So just negative 4.
No, negative 4 times that is 0. So
So that is 0. 0 minus.
0 minus 90, right?
Okay. I'm sorry. Yes. Okay.
So 0 minus 90. Okay, do the y component.
6 times 60. 60.
A is yeah,
Yeah,
60.
60. Trying to think of the component.
Mm-hmm.
Sorry, hang on.
Yeah, no worries.
60J. It's not negative, right?
Yeah, it's plus 60j.
Positive, and
Yeah,
then
that term is
minus-
0. Mm-hmm.
Right, because there's no Z for B.
Right.
You can tell I love cross products.
Mhm.
My favorite.
Mm-hmm.
Um,
Well, I mean, hey, everybody's got to practice, right? You don't forget, I got hours and hours of practice, right?
30K?
Okay, AX BY, so that's 30
Mm-hmm.
minus AY
40.
minus,
So
but that's minus
so
of
it'll be
minus.
positive.
Yeah, so it's 30 plus 40, 70. All right? Everybody agree? So it's minus 90I plus 60J plus 70K. That's the torque. Units are Newton meters. All right. All right, so let's see what does question C say. What is the time rate of change of the particle's angular momentum at this instant? All right, so what they're asking you is, really, do you know Newton's second law? This is Newton's second law. Time rate of change of angular momentum is given by the torque. You just calculated the torque. At this instant, that's the torque, and so that's the time rate of change. Okay? So that is the direction in which the angular momentum is changing, okay? And that'll be the change in angular momentum in 1 second, okay, if it maintains that change. All right.
How would you write the units for that one then?
For-
the time rate of change of angular momentum.
Okay, so torque is Newton meter, right? Angular momentum, what are the units for angular momentum? Oops.
So kilogram meters squared per second.
Yeah, and then if you divide that by second, kilogram meter per second square is newtons, and that would be Newton meter.
Okay,
Hmm. So it all works out.
thank you.
Yeah. All right. Okay, maybe I'll do 2 more problems and we'll do the lecture, okay? All right, do you want to do a neutron star problem? A pulsar is a neutron star. A wind turbine. A merry-go-round where a person jumps on. So that's a collision problem. And a space station.
Space station merry-go-round.
Mm-hmm. All right. All right, make sure you understand this problem as well. That's going to be on the exam. Yeah, so let's do the merry-go-round. Okay, I think the merry-go-round might be on the exam as well. All right, so a merry-go-round has a radius. Don't hold me to it. You don't hold me to nothing. So a merry-go-round has a radius of 2 meters and a moment of inertia of 300 kg meter squared. A boy of mass 50 kg runs tangent to the rim at a speed of 4 meters per second and jumps on. So yeah, he is jump 50. Okay. So it's initially at rest. What is the angular moment velocity after the boy jumps on?
This is conservation of angular momentum, right?
Yep. So this is a collision problem. In linear collision, linear momentum is conserved. Here, angular momentum is conserved. Okay. Very good. So Li, L final. Okay. So in this collision, angular momentum is conserved. Yeah. All right. So what we'll have to do is, so here the angular momentum is, so here's how you calculate the angular momentum for a point particle. This would be the moment arm, okay? So it's angular momentum initial is mv/r perpendicular, which is the radius of the merry-go-round. So 50 kgs times his velocity was 4 meters per second, and r perpendicular was 2 meters. Okay. So this is 400 kg meter squared per second. All right, final angular momentum is the moment of inertia of this system, the boy and the merry-go-round, times the angular velocity. Okay. So we'll write that here. LF is I final omega final. Yeah. All right. The moment of inertia is moment of inertia merry-go-round, okay, plus moment of inertia of the boy. Okay, and the moment of inertia of the merry-go-round was 300 kgs, and the mass of the boy times the radius squared. Because the boy is a point particle at a distance r. So 300 plus 50 times 2 squared. And this is all in kg meter squared. So that's 100, no, that's 200, so 500. Yep. So LF equal to L initial, I final omega final equal to Li. Omega final is Li over I final. Okay. And L initial was 400 kg meter squared. Yes. So this works out to 0.81 over second. Are the units correct? Omega. What are the units for omega?
Meters per second. Meters over second.
Radians per second?
Radians per second. And radians is a free label, so you don't have it. So that's why you just got 1 over second, okay? Do you guys understand that? So this was a collision problem where what was conserved? Angular momentum was conserved. Okay. All right, so this is a space station problem. This is very interesting. Can I have a sheet of paper? So if you read sci-fi, you'll come across this kind of stuff. So eventually this will happen for whatever reason. I don't think we'll ever leave Earth, but we might want to go on a long journey. And let's say if you go on a journey that lasts a few years, you don't want to be in zero gravity for a few years. You'll become mush. All your bones will collapse and stuff like that. So what you need is, you build a space station. It will be a cylindrical space station like this. You're living on the inside. You're growing trees, and the roots will grow in that direction. And the way you do this is, so this will be the space station. It'll spin like this. Okay. So the space station will spin like this. So you're here, you're going in a circular orbit, so that you feel centripetal acceleration. You feel gravity in this way. Okay, so because centripetal acceleration is like that. The ground is pushing you up this way, so gravity is acting like that for you. Okay, which way is the ground pushing you? Up. Gravity is down that way. Okay, so if the space station is pushing you this way, you feel a gravitational force in that direction.
So you're creating it.
Yeah, so you're creating it. It's artificial gravity. Okay? So the space station will spin like this. Okay?
Is it super fast and constant, like you can't stop, can it?
Oh, you want to switch off gravity, you just stop the spin.
But like, let's say, because you said they're growing plants on it, right?
Yeah, so it will be constant. Yeah, so yeah.
All times.
Yeah. So what will happen is, I imagine, so in the future, let's say 200 years, 300 years from now, these space stations will be revolving the Earth. So they'll be up there. And when you want to go on a journey, then you take off from there. And then you go wherever you want to go, and then you slingshot and come back to it. Okay. It will happen. Maybe that'll be your Disney ride for your grandchildren and stuff like that. Not funny, but it might happen. So a space station consists of a giant rotating hollow cylinder of mass of 1,000,000 kgs. Okay. Back 30, 40 years ago, this would not be conceivable. I mean, Elon Musk has made this possible with reusable rockets, including people on the station, and a radius of 100 meters. So this cylinder is roughly, the diameter is as big as this campus. Okay? Or at least from here to ISB. Okay? It's rotating in space at 3.3 revolutions per minute. So this huge thing is rotating 3 times a minute. In order to produce an artificial gravity, if 100 people on an average of mass 65 kg spacewalk to an awaiting spaceship, what is the new rotation rate when all people of the station are off. So this problem is the opposite of this. Here, this guy jumped in and he gave it an angular velocity. These guys jump off and the angular velocity decreases. Did you guys understand that? Okay. Now, here's the deal. See, when he jumped on, the moment of inertia of him was comparable to the moment of inertia of the merry-go-round. So the angular velocity change is noticeable. It went from 0 to 0.8 meters per second, radians per second. In this case, the mass of these guys, this is 100 people times 65, that's 6,500 kgs. This thing is 1,000,000 kg. These guys are like dust particles. Okay? Well, it's anyway, 0.1% the mass, so they won't change the angular velocity too much. And you don't want the angular velocity to change too much anyway, right? All right. You guys understanding this? Okay. All right, so we'll draw the space station first. And the space station is spinning, okay? So here's a side view. Okay, so we'll do so I initial was so a space station consists of a giant rotating hollow cylinder. So for this moment of inertia for the space station plus moment of inertia of the people, okay? And all the mass is at the rim. So this is mass of the space station times r square plus mass of the people times r square. 10 to the 6, 100 square plus 6.5 into 10 to the 3 times 100 square. Okay, that was the total mass of the 100 people. Okay, roughly 1% of the mass of the space station. Okay. So that works out to, okay, so that's 10 to the 8 and 0.0065 times 10 to the 8. Okay. No, 10 to the 10. That's 100 square. Okay, so 1.0065. Okay, that's the contribution of the space station. That's the contribution of the people. Okay. All right, what is the final moment of inertia? Well, the people have gone away. So it's only the moment of inertia of the space station is 1 times 10 to the 10 kg meter square. Yeah. All right, so again, what kind of problem is this? Conservation of angular momentum. Yeah. So I initial omega initial equal to I final omega final. Omega final is I initial So the final velocity increases by 0.6%. Okay? Mm-hmm. And that should be as it is, and that's how it should be. You don't want to change the angular velocity too much. Okay. All right, guys, so